Everyone, my name is Vishal Sharma and welcome to vishalfoodtech.com. Today's topic is advances in edible coating of fruits and vegetables. So we will basically see this is a trending technology, edible coating, and it is done to enhance the shelf life, decrease the respiration rate. So we will see what are the recent advances in food processing area regarding the edible coating. So basically, we know that fruits are classified as climateric fruits and non-climateric fruits. So climateric fruits basically they can ripen even after they are harvested and even after they are picked from the plant. And so they respire even after harvesting, and so more ethylene is produced, and it is detrimental for the food, detrimental for that fruit because it will be no longer be edible after a certain shelf life, after a certain storage period. Other are non-climateric, like they cannot ripen after removed from the plant. So once these non-climateric fruits are plucked from the plant, they will not ripen after that, and no ethylene production will be there. So basically our aim is to inhibit the rate of deterioration, and we have to change the gaseous environment that is present outside the fruit by any means, like we can use map, cap, like this. So we will see that later. So for example, we can use some packaging materials also that will prevent water vapor transmission, oxygen transmission also, so that respiration is reduced and the shelf life can be increased. So these are some of the techniques to reduce the respiration rate. So let us see some problems that are common in the post harvest area regarding fruits. Like first, the method of storage is too preliminary, like severe damage to fruits and vegetables happen during storage period, that we can see. Like if we are storing even in a advanced cold storage facility, even after there are some chilling injuries or other damage to the fruits. So storage is preliminary in the current scenario in India. And second issue is that we often use chemical methods to increase the shelf life to prevent spoilage, and those methods have some health issues also associated with them. And third problem is that reduction in edible quality of the food products due to biochemical changes, and some microbial infections can also cause the reduction in edible quality. So what are the solutions to these problems? So first solution, as we all know, map and controlled atmosphere is already available, but it is also most effective, but it is quite expensive, and not every individual, every farmer can adopt these methods. Here we can see a map instrument is around 12.5 lakhs per unit. So this is comparatively higher price uh, for an individual. And the second solution can be low temperature storage. It is also quite popular, leading to it, but one problem is that it leads to chilling injury and heat treatment if it is not properly utilized, and also weight is also decreased somewhat, or flavor or vitamin losses are also prevalent in low temperature storage. Third solution is we are going to talk about is edible coating. So edible coating, we will see it can control and inhibit the changes that are deteriorating, and they can increase the shelf life, and they can also help to solve the post harvest losses. And edible coatings have mechanical effect, like they are somewhat strong, they have thermal effect, they can withstand some temperature range, and they are also antimicrobial, and even antioxidant properties can also be incorporated into the edible coating. So here we can see, this is an example. This is first figure is before coating. This is directly plugged from the farm, and in the second figure we can see this is coated, edible coated, and after 14 days the control sample is has started deteriorating, but the coated sample is not affected as much. And after 28 days we can see the coated sample, edible coated sample was like that before 14 days, and but the control sample has completely deteriorated. So this is the advantage of edible coating, and edible coating is harmless because only polysaccharides, carbohydrates, and other saccharides are only used, and they are all edible. Here also an example of edible coating. This is some powder is coated with edible coating material. This is not a fruit, and this is the strawberries that are coated with edible coating material, we can see here. Now we have to see the classification. Edible packaging, we know that they can be eaten and they have a biodegradable ability. They also have barrier properties. So there are two classification: edible films and edible coatings. Edible films, basically they form a thin layer around the food product, and edible coating are made from biodegradable materials like lipid, protein, polysaccharide. So basically we are going to talk about edible coatings only in this video, not edible films. So these are some of the definitions of edible coating. So I am going to read only the first definition. Like, this is a thin layer of edible and environmentally friendly material that can be consumed, and they provide barrier. Also, we can also see third definition, like it is enrobing of food material either by dipping of material into the filmogenic substrate or by spraying the same over the food as an edible coating. So we will see this, like we can dip the fruit into the solution, or we can also spray by using some sprayers on the fruit. So shelf life is increased, and the thickness basically ranges from few microns to few millimeters. Now this is an example, like fresh cut fruit is that this is a fruit and it is ready to consume. Now if we store it for some time, we can see some deteriorative effects started coming into the fruit, and this is basically uncoated fruit, and after some time it will spoil, it will get spoiled. But if we coat it, if we put it into a filmogenic solution, that is, this is also edible coating only, that is, in edible coating we put or dip into filmogenic solution. So after putting it, we can see that after a certain storage period, these fruits are as it is like before. So this is the advantage of using the edible coating. Now this is another example. Control sample is there, and after 10 days this is deteriorated, but the coated sample even after 16 days is looking red and fresh, and after 21 days some deterioration is started happening, but yet it looks somewhat edible and easy to use and safe to use. Now let us see the mechanism of edible coating. Like, we know fruits and vegetables continue to respire even after harvest. Like, we are talking about the climatic fruits specifically here. And then what we have to do to prevent this, we have to create a pseudo atmosphere around the fruits. So this is provided by using edible coating, and it will prevent the water loss from the fruits to outside. And this results in low oxygen and high CO2 atmosphere in the pseudo atmosphere that is created. So anaerobic respiration is started, and low oxygen atmosphere basically in the pseudo atmosphere will disrupt ethylene production, and the ripening is delayed, and hence the shelf life is increased. Prolonged firmness is there, and freshness is also maintained. So basically, if I talk about the edible coating classification, basically coating can be either polysaccharide or animal plant protein or lipids also, or agro industrial waste like fruit residues we can use, or like peels of some fruits like mango peels we can use as an edible coating also. These are some of the examples. Another, composite materials like mixing of polysaccharides and protein we can mix, or polysaccharides or lipids we can mix. So these are some of the classification, and we will be going to discuss in detail about these. So let us see first the polysaccharides, that is the edible coatings which are made from polysaccharides. So we can see examples like pectin is also polysaccharide, cellulose, starch, chitosan, alginates. So but one disadvantage is that they form a poor barrier against water vapor because they are hydrophilic, that is water loving, and they are commonly used to improve shelf life of meat products, vegetables, and linear structure of some of the polysaccharides like cellulose, amylose, and chitosan renders their film toughness, flexible, transparent, and resistant to fat and oil. So basically, this is an example. Apple is dipped into a polysaccharide film forming solution, and polysaccharide is also added there, and some inorganic nanoparticles are also added. These inorganic nanoparticles are basically added to enhance the quality, to enhance firmness, flexibility as desired, and as according to the function that is provided by that nanoparticle. So after coating, we can see this is the maximized view, and we can see the coating. A fruit is red color, and the blue color, sky blue color, is the film, and inorganic residue is that after the blue color. So this is the structure of the edible film that is coated. Now cellulose derivatives are also used as an edible coating, like carboxy methyl cellulose is there, methyl cellulose is there, hydroxy propyl methyl cellulose, HPMC. These all are used as an edible film, edible coatings. And advantage is that they possess good film forming characteristics, like the filmogenic solution that is prepared is having good properties. They do not smell, and they are having no taste. They are flexible also, and strength, transparent, and resistant to oils and fats. Now let us see, this is a cellulose based film that is coated on a mango. So fruit is mango yellow in color, and a coating is blue, dark blue in color. And if we maximize it, we can see citric acid is also present in the coating, and probiotic bacteria, because we can add some value addition, or we can add some antioxidant, nutraceuticals, anything that is good for the fruit, good for the edible film, edible coating. So probiotic bacteria is also added there, and CMC, carboxymethyl cellulose, and hydroxyethyl cellulose is also present in the coating. Now if I talk about the starch, basically starch, we know that storage polysaccharides, and they are used to produce biodegradable films, and they are replacing the plastic polymers, because starch is basically low cost, and it can be renewed, and mechanical properties are also good. So basically one example of starch is that high amylose starch such as corn starch is a good source for film formation. And here we can see this is an example of starch polysaccharide, transparent. This is looking transparent, and these are edible film from amaranth starch. So this is a type of film, not coating, but this is shown just for example. And we can see that the coating is also transparent. So this is a property. If we want transparent coatings, we can use starch as a material. And one problem is that starch does not alone form films with adequate mechanical properties. We have to add some plasticizers. So main challenge is that the starch, if we make only starch edible coating, it will be brittle in nature and it breaks easily. So what we have to do, we have to add some plasticizers, like examples are there, like starch. In starch we can add glycerol and other low molecular weight polyhydroxy compounds like polyether So when we use plasticizers, the flexibility is there and brittleness is reduced to a greater extent. Now this is another polysaccharide, chitosan. Basically these are obtained from shells of shrimps and fungal cell walls and their structure is similar to cellulose. Here we can see from the waste shrimp shells the chitosan is obtained. Here we can see white color powder is there. And if we want to do some value addition to our edible coating or some beneficial effects, so we can use here it is using the byproduct of tomato plant, and it is extracted and made into a solution, and both are used to make the filmogenic chitosan edible filmogenic solution, and they are used to coat the pork meat, which is then packaged and refrigerated. So control, if the pork meat is there without coating, it will be there for shelf life of 8 days only. But if we coat it with this chitosan edible coating tomato plant extract, we can see the treatment is increased. Treatment shelf life is increased up to 21 days. So this is the benefit of using edible coatings. Another polysaccharides are like alginates and carrageenans. So basically these are, where the definition we can see salts of alginic acid, which is a linear copolymer of D-manuronic acid and L-gluuronic acid monomers. So one example I can show here, that if we use the alginate and carrageenan coating on strawberries, on the day 0 this is looking like this, control sample and coated sample. Left is the control sample, coated sample is on right. So after 6 days the control sample started deteriorating, but the strawberry which is coated from alginate and carrageenans are as it is, and they look fresh. And even after 12 and 15 days also the freshness is maintained in the coated sample. Carrageenan, we know that they are obtained from seaweeds, and they can be used as a thickening or emulsifying agents. And carrageenan has different polymers, and they are named as alpha carrageenan, kappa carrageenan, example, etc. So basically, kappa carrageenans and sodium alginate, they can be used as a class combination for better edible coating materials. Here we can see example, alginate is used and carrageenans both are used to make the edible films. And for some value addition property like antioxidant property, the cinnamon extract oil CEO is also added, and they are cross-linked by using Ca+2. So the edible film that is created is having high mechanical property, antioxidant property, and antimicrobial property also. And these are some of the results of this edible film, like the increase in kappa carrageenan ratio in the sodium alginate based matrix, however decrease the mechanical property, and power absorption or flexibility was increased in the edible coating. So crystallinity index is also decreased, we can see from the third point, but in the fourth point we can see mechanical properties reduced, but improvement in film flexibility is also there. So based on these requirements, we can use different type of polysaccharides for our edible coating. Like if we want more flexible, we can use this. And pectin is also the one of the polysaccharide, and it is also used for edible coatings, but it is not commonly used alone. It is used with some plasticizers and some other extracts. Like here beetroot extract is there. If we use a beetroot extract and pectin, we can use a top edible film like composite film. If we use only pectin as an edible coating, you can use this. And these are if we use the red cabbage, the edible coating that is created is that. Now protein based coatings we can see here, like casein is there, gluten, soy protein. We will discuss one by one. These are the classification of protein. Like we know fibrous proteins are there and globular proteins are there. So fibrous protein, basically we know these are water insoluble, and examples are like casein is there, whey protein is there, collagen which is found in skin, hairs. Collagen is not in keratin is found in skin and hairs. Gelatin is there, collagen, and globular proteins are there, like they are soluble in water. Example, wheat gluten is there, soya protein, peanut proteins, cornzein, and cottonseed proteins. So basically we are going to study somewhat these protein based edible coatings. As we can see, gelatin. So gelatin based proteins edible coatings and films are basically obtained by controlled hydrolysis from fibrous insoluble protein collagen. And collagen, we know that it is a major constituent of skin, bones, and connective tissue. And here the gelatin films and coatings basically has these composition, like plasticizer we have used 10 to 30%, 40 to 70% water, etc. And it has applications, like it has used to encapsulate low moisture or oil phase food ingredients. Basically in pharmaceutical it is used. And corn benzene based coatings are basically they are having good water vapor barrier property and compared to other edible coatings. And zinc coating has an ability to reduce moisture and firmness loss. Here we can see one example, like orange peels are there. So we, as I have already mentioned, that we can utilize and we can valorize the other waste products like orange peels. We have done the ultrasound treatment, and then after distillation the orange peel extract is obtained. Now it is mixed with the gene protein, as we can see, and we have obtained the film forming solution. And for some more value addition and for improving the thickness, and as a thickening agent, the cornstarch is also added and the composite film is obtained. Now another polysaccharide is wheat gluten, and edible films can be formed by drying aqueous ethanol solution of wheat gluten. And here what happens, like the SS bond, disulfide bonds are there in the gluten. So during kneading or during the processing, the disulfide bonds are broken down. During heating also it can be broken down, and new disulfide bonds are created afterwards, and in the intermediate the SH bonds like sulfide hydryl bonds are created. So these are some of the steps, like first disulfide bonds are broken, SH bonds are created, and then the new SS bonds are created, which provide new improved mechanical strength. Here we can see first wheat flour is taken, and we know that how to separate wheat gluten from wheat flour. So what we have to do, we have to knead it, knead a form a dough, and we have to start rubbing into in front of the running water, and starch will continue to flow along with the water, and what we have left in the is the gluten, wheat gluten. So basically starch and gluten are separated, and we put it into a casting material, and we can obtain starch films if we use only starch. We can obtain gluten films if we use only the gluten that is obtained, and it can be used to coat, it can be used as a coating on carrots. Now this is a soya protein, we can also use is as an edible coating. Most of the proteins in soybean is insoluble in water but soluble in dilute neutral solution. And here these are the classification of edible film based on soya protein. Can be produced in surface film and film formation from solution of soya protein isolate. Now to form the coating from both soya milk and SPI, we have to heat the solution to disrupt protein structure, and then after heating the disulfide bonds are broken, and then the SH bonds are exposed, and then the new disulfide bonds are created, which are more hydrophobic, and the hydrogen bonds are also created during the drying of film or coating, we can say. Soya protein coatings are also similar to the films. Now here is an example, like soya protein isolate is there, and it is mixed with licorice residue extract, and the resulting film or coating is the antioxidant film is there. And what we have done is that we have introduced or some antioxidant property also in this film, or we can do this in the coating also. So this film will do, it will quench the free radicals that are generated and hence prevent the oxidation. Casein is also a milk protein, and it can be used as a coating or film. For example, this is a company Lactips which has developed an edible plastic made from milk protein, and it has enormous potential for intelligent packaging. And keratin is also there, used as an edible coating or edible film, like chicken feathers are first dissolved in the solution, alkaline solution, and then after precipitation the film look like this yellow colored bioplastic film, and they have good mechanical properties, but relatively less than other proteins. Another is whey protein. Basically whey proteins, we can see here, these are the films that are shown, and these are biodegradable in nature and used in food and drug packaging. Lipid based coatings, basically the most effective lipid substances are paraffin wax and beeswax. So these are used as coating for different food products, and these are the classification, like most commonly used lipid based coatings are wax and oil based coatings, fatty acid and monoglycerides, resins and rosins, and emulsions. Now these are some of the classification of wax, like wax is animal wax can be there, like bee wax or insect wax, and vegetable waxes or minerals and synthetic waxes can also be there. So we can utilize wax as other edible coating apart from oil based coatings, and fatty acid and monoglycerides, as we all know, it can be used as an coatings. Example, emulsifier, we can use emulsifier as coating also in the fruits. Dispersing agents can also be used as coatings. Resins and rosins basically are included in edible coatings, and the examples are like wood rosin and comaronandine, both are which are used in coating citrus fruits. Emulsions, basically as previously discussed, it can be used. And what I have said earlier, like antimicrobial agents and nutraceuticals are also now quite popular, and they are included in the edible coatings so as to enhance its property, reduce the microbial prevalence, and nutraceuticals are also added. Here one example of coating is there, like these watermelons are coated with this edible coating that is formed from polymer support, and nanostructured lipid carriers are mixed with solid lipid nanoparticles, and the food that is and the coating that is created is like this. It is having rich bioactive compound that is released because of the nanostructures are also quite popular in use for the edible coating preparation, and they release bioactive compounds as desired into the food material, into the coating also. Now, how to apply the edible coating or films? First, we can use a directly dip, but this is short. We have to do it in bulk, like lots of fruits in bunch. We have to dip in mechanical, like manufacturing lines. Dipping is also used for larger lots, but yet some disadvantages are there. So this is a procedure like complete wetting is of the surface of food material is there in dipping, and product will absorb the contents of the coating solution, and a protective layer is created, and the coating solution then finally drained out. It is removed, and the fruits that are coated are dried, and then brittleness problem basically is there. So what we have to do, we have to use the plasticizers as already discussed. This is an example. Fresh fruit is first put into filmogenic solution, and then the coated fruit is taken out. Drawback is that we have to replace frequently the solution. Again and again we have to replace, and what we have to do, like regular replacement and ensure it is properly mixed or not, and these are some of the disadvantages. So another method is that we have overhead drip emitters, like it is like a spray solution only, like fresh fruit is there and sprayed, it is basically sprayed, and the coated fruit is there is a rotating brush onto which sample is mounted, ensures development of uniform coatings. Another is spray technique, like filmogenic solution is filled in a spray bottle or a automatic spray nozzle in for larger manufacturing facility, and then it is sprayed on the fresh fruits, and coated materials are taken out. Parameters we have to maintain, like viscosity of the filmogenic solution, the temperature at which the edible coating should be properly fixed to the fruit, it should stick to the fruit and form a protective layer. Applied pressure should also be taken care of, and nozzle characteristics, like at what thickness the nozzle is spraying the filmogenic solution onto the fruits. This is an example of spraying. This is a spray bar, and it is a spraying on the fruits, and the layer is created. Another method is layer by layer method. We can see fresh cut fruits are there, and they are firstly dipped in mucilage anionic solution for 2 minutes, then dried for 2 minutes, then put in cationic solution for 2 minutes, and then dried and packed. These are some of the examples of layer by layer method. Vacuum impregnation technique is also there. Here the temperature pressure is reduced, so basically vacuum environment is created and food submerged in an airtime vacuum. It is similar to dipping, but here pressure is reduced and vacuum is created. These are some of the coating materials for different food products, like alginate and chitosan are generally used for guava, and pectin is used for tomatoes, etc. And these are some of the advantages, like we have already discussed: reduces weight loss, reduces respiration, prevents food from chilling injuries. Problems, we can see that sensory implications may happen, like sometimes it hardens, or sometimes the consumers do not like the coating, sometimes there is a thickness is not as per desired consumer want, so they can create some challenge. Food safety issues can also arise, and allergy, some consumers have some allergy, like use gluten intolerance is there, and gluten edible coatings are coated onto the food, so it can create some problem. Other is like it is somewhat costly, like we have to use the polysaccharides, and we have to spend some time and time to coat, because it is time consuming also. So basically overall the cost factor is also included into that. Now talking about the future trends. Now this new generation of edible coating is under development, which aims to incorporate and control release of active compounds using nanotechnological solutions such as nano encapsulation and multi-layered solution systems. So basically, as I have already discussed, control release of bioactive compounds is quite trending, and using the nanotechnology, the edible coatings are slowly releasing some bioactive compound on into the fruits, and that is beneficial for the fruits and for health. So basically, nanotechnology used to enhance nutritional aspect of food by means of nanoscale additives and nutrients and nanosite delivery system for bioactive compounds. And micro and nano encapsulation are also used nowadays. And here we can see alginate is most commonly used material for encapsulation. And but materials from other sources can also be used. Enzymes, probiotic, prebiotic, marine oils, etc. are most suitable functional substances to be encapsulated. And we can also prepare multi-layered structures, because we can do continuous dipping, then drying, dipping, drying. These are called multi-layer structures, and these are also quite trending and future trends. They have good scope. And coating foods with nanolaminates involves either dipping them in series of solutions containing substances that will absorb by the food surface, or spraying substances onto the food surface. And these nanolaminate coatings could be elaborated entirely from food grade ingredients, and could include various functions such as antimicrobials, anti-browning agents, antioxidants, enzymes, flavorings, and colorants. So these are all some details about the edible coatings, and you can go and see some of the references as mentioned here. Thank you so much. If you like this video, you can share this video with some of your research scholars who are working on edible coatings or films, and you can also share with your friends. Thank you so much.